Hey guys, good morning. So today we're gonna start our last topic of the course. It's called super vector machines or SVMs. So we're gonna have it in 4 lectures. So today, Friday, and next week, Monday and Wednesday, I guess. And so let's start talking about SVMs. All right, so support vector machine, as you see, so there's an example on the top right side of your slide. So first of all, they are a classifier, right? They classify data for us, much like those linear classifiers that we learned throughout the semester, perceptron, and then stacking them up to build a neural network, MLPs, and other things, right? So they're also a classifier. And what they do is they formally define by separating hyperplane. So hyperplane, so this is in, think about this in two-dimensional, right? Instead of being a line, if you look at it this way, if you look at the line this way, so this is going to be in hyperplane, right? And in higher dimensional space, the hyperplane could have higher dimensions as well. So they use a separating hyperplane like that, and just like any supervised learning method, given label data, the algorithm will output an optimal hyperplane, right? Instead of aligning perceptron. So that sort of bluish area around that line is sort of a safety cushion that SVMs use in order to avoid overfitting. We talk about it more. So think about this as a safety cushion, right? So we want this safety cushion to be as large as possible, or what we call it in SVMs, as fat as possible. So this is a fat hyperplane, which is preferred than the other one. So in 2D space, in what you see in this figure, the hyperplane is a line dividing a plane into 2 parts, right? Each of the classes lay in either side. So that's a pretty much very high level definition for SVMs. All right. So now that we know that they can define by separating hyperplane, and the fatter the size of this safety cushion, the better. So let's see how we're going to define each of those elements, right? We want to make sure that this distance will be the highest, your error would be the lowest, right? And you compute and think about this as sort of a plane, right? So those points are perpendicular actually to this plane, right? So these points are here, right? And all of them are perpendicular to the surface of the hyperparameter, right? If we define a unit vector here, right? So we talk about those today. All right, so let's see how we're going to define an optimal hyperparameter. So we have 3 different classifiers here. So look at the one on the top left most. So suppose these two data are noisy, right? That's why you're going to have you see a circle, a gray circle around those. So it shows that they are prone to noise, which is pretty much on every data. Suppose they're coming from a sensor and a sensor is always, prone to noise. So instead of one X, like all at the same point, you might have different X's, right, surrounding. So that shows the noise. It would be great if our classifier, which is that line, right, this line, could perform in a way that if the noise got bigger and bigger, right, it wouldn't misclassify actually. Because if the noise gets bigger, after this point, this area would get misclassified, right? So we're going to have error here. So going on the middle side, the noise is higher, and also this one is the highest, right? So if the noise is the highest, we actually needed to change the weights of this hyperplane in order to cope with the new noisy data, right? So at every point you see that the W's are different. So what if on the other side, instead of dealing with the noisy data, we expand the safety cushion of the perceptron itself, or the hyperplane in SVMs, right? So here you see for the same data, you have a very slim hyperplane. This is fatter and this is the fattest one. So this is the fat one. And that's exactly the intuition behind SVMs. We want to make sure that we find the fattest hyperplane that classify the points correctly, right? And by computing this distance, which we later call it rho or theta, depends on the convention, we can define our SVMs. All right. So just like what you saw in the previous slide, we have two separators, right? L1 and L2. In both cases, you see that the classification error, the E in is 0, right? Because all my -1 class has been correctly classified on top of the line, and my +1s are behind it. So the error in both cases is 0. However, because of the noise margin that the right-hand side had, right, we changed the classifier in a way that to cope with such data. So intuitively, you see that L2, the line L2, classifying the same data, so different line. L2 is more robust, right? But in both cases, we have no error. Okay. So let's see how we're going to calculate this classifier margin, right? So as always, we define your data as a set of D which contains x1, y1 up to xn, yn, and they are having two different classes, so two labels, -1 and +1. It's a binary classification. So assume that y was a signal, so it's a sign of wtx plus b. He has your biases. Just like what you had as W0 before. Be our decision rule, right? Given this d-dimensional R space. And also B is within R set of R, right? So we define L, so let L, that line that classifies as WTB plus X, corresponds to the decision boundary, right? So if you think about that line that I described in the first slide, so that was actually from this view was a line, but actually it was a hyperplane, right? Think about it as this hyperplane. And your point is on top of that, the pluses. The minuses are behind, right? So your hyperplane is here, and the points are above. So if you want to make sure how you're going to compute the margin between your data and your hyperplane, so you have to compute this W, which is perpendicular to the unit vector of the surface, right, of this hyperplane. Just like before, so suppose, so this is a unit vector, right? We can call it U or anything else. So unit. This is 1. So you can pick any points on the surface, such as x prime, and then these points are perpendicular to this. So if you want to compute the distance, right, we call it dist, function of dist, of your x's above and beneath, so you need to have the absolute value of Wt xi plus b divided by the norm of that W, right? Because so let U is a unit in general, thus so you would have the distance of x and x h as ut x prime. So that would be the projection of your x prime vector, right? So the projection of this vector x and x prime would be ut, if you consider this one as u, x minus x prime. And that's why you can compute this, divide both by the norm of W, and you're going to have the margin between your points and the hyperplane, right? So that's actually the projection of the vector x minus x prime vector onto u. To u. So now we know how to compute the distance between our x's and the hyperplane, right? So the other issue would be how we're going to maximize, how we're going to find the fattest margin between those. Before that, let's just have a quick convention set. So if you recall in the previous lectures, we would always use the bias as a W0, right, and 1. So in X we would use the 1, and for the value we would use W0, right? But in this chapter, in SVMs, we add it as another separate value. So you have B in your formulas, right? So this sign WTX, or the signal of WTX becomes WTX plus B. Which is no big deal. Okay, so now let's go back to our hyperplane. So if you're talking about the binary classification, right? So we have two different classes, pluses, minuses, or here we have circles and crosses, right? So the point, this is our hyperplane. That correctly classifies these 2 points, right? We can see that in both cases, we have always, this statement always holds. Which is when the label of the class multiply WG n plus B, right? This is always positive on both classes. Why? Because on the other class that was -1, so here, right? +1. Why? You see, if you multiply that, it's going to be minus, multiply minus, it's going to be positive. And on the top of the hyperplane, the +1 class also make this positive as well. So in both cases, this value always is positive, right? And we're going to use this property in order to define the exact margin later on. All right, so this is just the formal definition of what I mentioned in the previous slide. So we have always this value positive for our yi's in a set of -1 and +1, the binary class, right? And the value of the yiwtxi plus b is equal to the absolute value of wtxi plus b, right? The magnitude. And we also mentioned that the distance, we can compute it by dividing this value to the norm of w, right? To find the distance between our x's to the hyperplane, right? So we have these three values now, these three formula. Now we can define the margin of the classifier. Yeah, this is all right. So let's carry on. So we define the minimum distance between our x's and the hyperplane that we define by a value, a parameter called p or rho of L for all of our i's from 1 to n, right? So suppose you have these two set of data and the blue line was your hyperplane. So this is your hyperplane, right? So the rho of L is the minimum distance for x and L, right? The closest, you need to find the closest point. In this case, it was this minus, and in that case, it was a plus. So that you still would be able to classify correctly, right? Because of these 2 points, I can define a rho or P that is a margin of my hyperplane, right? as we knew, the signal yn was WTX plus B was always positive. However, we didn't know that the magnitude, right? The magnitude would be small or large. So scaling this P would be the same as well. So we have another set of data here as well, right? You can compute the P, the margin to the closest data, right? Plus and minus. Okay. So now let's define the support vector machine or the SVM. So in general, we need to find a classifier that maximizes the margin, right? That's a very high level definition for that. So we need to maximize that margin P or rho we found. In order to do that, we need to do a key normalization. So let us assume WTX plus P is 0, right? This shows that that was a decision boundary that correctly classifies each point. And we knew that this value is always positive because it was correctly classified. So finally, we want to define a delta that minimizes yn wtxn plus b for all the n's from 1 up to n, right? So for any separating hyperplane, it's always possible to choose weights so that this signal, this one, or the magnitude greater than, or equal to 1. So now if you make sure that this delta is the minimum value of this, that's exactly find our classifier that maximizes the margin. Okay. So clearly we know that delta should be positive. So we will always have to choose a W and B, which are the parameters of our hyperplane, right? Clearly. the parameters of our hyperplane. So params such that we find delta equal to 1 without loss of generality. So this word is also called WLQ, it's the abbreviation, VLOG, right? All right, so why without loss of generality? Because suppose W wasn't 1. So let's think about it. Let's prove it by contradiction, right? So suppose suppose delta wasn't 1 for a given W and B, right? So let us assume another W and another B, right? Two different values for the case that delta wasn't 1. So in that case, we would have had another L, we call it L prime, that denotes the same decision boundary as L, right? So for L prime, the new L prime that we derived from the two other values, W and B, we can see that the minimum of Yn, which is the output of the signal of the classification, is always equal to 1 divided by delta, minimum of this amount, if you divide them both by delta, right? And then the final value becomes 1 again. So we can see that we can prove it by contradiction, because we thought delta is now 1, and now it's 1 again. So that's why this holds. So in SVMs, we always have to find those W and B, those W's and B, such that delta, or the minimization of that formula that I mentioned in the previous slide, is equal to 1, right? Okay. So again, without loss of generality, any decision boundary can be finally represented as the following. Okay. So I'm interested in minimizing Yn Wt xn plus b equal to 1. And I can compute the distance, find a closest point, right? Minimum distance of xn and L, which was equal to delta divided by the norm of W. And we saw that this is 1, so it's always equal to 1 divided by norm of W. So the largest margin we can find is the maximization of the value 1 over W. right? It's the other way around. Okay, now we set up our constraints. So we finally can define the formal problem for SVMs. All right, so, and that would be the equivalent formulation. There's a proof with that, but you can find it in your textbook. So in general, that's our final problem. So that's the equivalent formulation of that maximization equal to 1. So in general, for SVMs, we need to compute the minimization of 1 over 2 W transpose W such that Yn WT xn plus b is always equal or greater than 1. So this is the problem we need to solve. And for SVMs, this will yield a quadratic programming issue, right? So QP. There are many QP solvers you can use to solve bigger problems, but in small problems, what you need to do is just find your constraints using your x's, the matrix of x's, and the y, the label, and for each of the lines, you generate this constraint, right? So you would have 3 lines of this, like -1, depending on the label of y and your x. You have like W1 plus multiply the x you had, and also the value of Yn comes from this matrix, and you would, set it greater than 1 or equal to 1, and you would have like 3 different lines for this case, and you would solve it using a QP solver or just by hand manually, and that would give you the SVM for that problem. So another reason that we call this an equivalent formulation is because at minimum, right, at minimum that value we'll have an inequality, right? This is at minimum is going to be equal to 1. So we don't lose anything. That's why we can use it as inequality. Is it clear so far? Okay. So let's prove it again by contradiction. So let assume let W star and B star be the optimal solution, right? And you suppose your theta is the mean for all the n's of this value, W transpose xn plus B star, and the value is greater than 1, right? So let W, you have divided these two by theta, you normalize it, right? Since your norm of W is always smaller or equal than 1 over theta W star, and this value is always smaller than W star itself, and we knew that the case was correctly classified. Thus, we're going to run into an issue right, and it contradicts. Thus, the proof still holds, right? This is proof by contradiction. Because this shows that W star cannot be optimal for the value 1 over 2 WT so it cannot be optimal unless W star is 0, which is not possible, right? Because if W star is 0, we cannot correctly classify this. But we know that it was correctly classified, so we run into a contradiction. And we can prove this that by contradiction. Alright? Any questions so far? So by now we know that we would like to have a fatter margin. SVMs generate a hyperplane that computes the distance to the nearest data at each class. And in order to solve SVM problem, you need to solve this minimization problem 1 over 2 WTW such that this condition holds. Alright? So next session we're going to carry on with other properties of SVMs. Alright guys, have a good day.